So we are going to solve a first order linear equation using an integrating factor. If we go back and look at the definition of a linear equation, a linear equation is defined as one where we have some function bn of x and the nth derivative n minus 1 of x, the n minus first derivative, all the way up to some function b1 of x, first derivative, and some function in terms of x and y. And that could equal to 0, it could equal to, what just happened here? Equal to 0 or equal to f of x, some function. Now, we're only going to look at a first order linear equation, so we don't care about the higher order terms. So the first order linear equation will simply contain those terms. And as I said, f of x could be 0, and if it is 0, things are pretty easy. So, suppose we have a function of that sort, and we have b1x, I'll use lowercase, the first derivative, I'll call it y prime, b0 x, y equals f of x. I'm going to divide both sides by b1 of x. And the right-hand side is yet another function, so I can rewrite that as, say, g of x. And the function here is also another function, so I'm just going to call it p. I believe that's the textbook notation, and I'm trying to be consistent. So the dE now reduces to the simple form y prime plus py equals g of x. I'm going to multiply both sides by mu, and that is called the integrating factor. So the dE would now become mu y prime plus mu times p times y equals mu times g of x. To solve this, we've got to do a trick. In other words, if we have a condition, the condition being mu p equals d mu over dx. If that is satisfied, then we can rewrite the equation in this sort. So we have mu prime plus mu p times y, that is our original dE, and the condition is mu p equals d mu over dx. If that is satisfied, I could rewrite the dE as mu y prime plus d mu over dx y equals mu times g of x. which would mean we have mu times y prime plus mu prime y equals mu times g of x. If you closely observe that particular equation, which we simply took the original differential equation, we imposed a condition, and that is the condition. If that is satisfied, the original first order differential equation turns into mu y prime plus mu prime y equals mu times g of x. Now, the left-hand side of that equation should give you an idea if you think about calculus, calculus 1 to be clear. So if you observe that carefully and recall product rule of derivatives, what does the product rule state? The product rule simply states if I have d over dx of some function u times some function v, we have u v prime plus v u prime. In RDE, if I set u to be equal to mu and v to be equal to y, then the right-hand side, if you plug that in, you would simply get, the left-hand side, which is mu y prime plus mu prime y. So what do I mean by that? So u is mu, so you have u v prime plus v or u, must have made a mistake somewhere here. Let's go back. And that is mu prime. U is mu and v is y. So we have u v prime plus u prime v. And that directly relates to the product rule that we have. So if the condition is satisfied, the right-hand side, the left-hand side can be rewritten, and we could rewrite it as d over dx, u is mu, and v is y. And that would equal to the right-hand side. I keep confusing the sides. So that would come right over there. So the trick here is that condition mu p is equal to d mu over dx. So the first step is to solve for that integration factor. We already know that our condition is satisfied, or our assumption is true. So based on mu times p equals d mu over dx, I could solve for mu. If you observe carefully, that is a separable equation. P is a function of x, and mu is mu itself. So we can move all the mu terms to one side and p and d of dx to the other side. So if I rewrite this, I could rewrite it as p times dx equals d mu over mu. And if I integrate on both sides, I will get p times dx equals d mu over mu is ln of mu. And we have a constant c. we want to solve for mu because that is the integrating factor. We call it the integrating factor because I'm going to because there is an integral over here. So I'm going to exponentiate on both sides. So I would have e raised integral p times dx equals e raised ln of mu plus c, which, if I use the rules of exponents, so I would have e times ln, e raised ln of mu times e raised c. The exponent and the natural logarithm would go away, and e raised c is also a constant. C is a constant of integration. Let's say if the value of c is 2, then e squared is also a constant. So I'm going to just call it as, c1. So we would end up getting e raised integral p times dx equals mu times c1. Later on, we would see that this particular constant doesn't have much of an influence in the final solution. So we're going to make another assumption that c1 is simply 1. You may ask me, well, why is he doing this? Well, if we plug it back in the solution or in the differential equation or the eventual integration part, we will end up getting the constant of a constant thing, just like we had c to be a constant and e raised c as a constant. So I could rewrite e raised c as c. So eventually we'll get too many constants and, why not get rid of a constant? So what we have done thus far is find that right over there. In other words, we have solved for the integration factor, but we did not solve for the differential equation itself. So to find the solution of the differential equation, we go back to where we started, which is right over here. After all the things that we did using the product rule, the assumption, we took the original dE and we rewrote it that way, d over dx of mu times y equals mu times g of x. So I'm going to go back to that equation and rewrite d over dx mu y equals mu of gx. I'm going to plug in the value of mu. So I would have d over dx e raised integral p dx times y equals mu times dx. So here, y is dependent on x. And I could multiply by dx on both sides. So I'd have d of e raised integral p dx times y equals mu times g of x times dx. If I integrate on both sides, e raised integral p dx will be a function of x because we are integrating with respect to x. So it is simply going to be some function of x. So I can pull that e raised integral p dx outside and write it this way. and integrate on both sides. So I would have integral e raised integral p dx times dy equals integral mu times g of x dx. Now, as I mentioned, we are integrating with respect to y, and that part right there is a function of x. So if we are integrating with respect to y and the integrand is a function of x, it would be treated as a constant, so that is going to come out. So e raised integral p times dx integral dy equals mu times g of x dx. On the right hand side though, when I rewrite mu, well, on the left hand side, integral of dy is simply y. The right hand side, mu is e raised integral p dx times g of x dx. I can't pull e raised p integral p times dx out of the integral. The reason being, the integral is with respect to x. That is a function of x. That is a function of x. So we have to integrate the entire expression. So there is nothing we could do about it. We will leave that as is. So divide by e raised p dx on both sides. We will get y equals 1 over e raised integral p times dx, and the entire right hand side integral of e raised integral p dx times g of x times dx. In a simple way, we could write this as y equals e raised negative p times dx integral e raised integral p dx times g of x times dx and plus c, a constant. So that would be the solution to the linear equation. So let's look at the first problem here, and I am going to do this in two different ways. If you look at the equation dy over dx equals 5, that seems to be a straightforward separable equation. Now, we don't want to use the approach that we are employing here for a separable equation, because this method is a bit more complicated than simply using the technique of separable equations. So if I use the separable equation method, I can move all the y terms to one side, x terms to the other, integrate on both sides. Integral of dy over y is simply ln of y. And 5 integral of 5 dx is 5x. And we'll throw in that constant plus c. So I will exponentiate on both sides, so e raised ln of y equals e raised 5x plus c. The e and ln would go away, so y would equal to e raised 5x plus c, which I could write it as e raised 5x times e raised c, using the property of exponents, and since e raised c is a constant when c is a constant, I could simply write this as some constant, say b, times e raised 5x. So that is the solution by using the separable equation method. Now let's see how we can complicate this by using, integration factors and such. So the same problem can be done using the linear equation approach that we just went over, and we have dy over dx plus 0 times, minus 5 times y equals 0. So going back to our structure over here, the equation, the one we rewrote, is dy over dx, or y prime, plus p times y equals g of x. By direct comparison, we'll compare this to y prime plus p times y equals g of x. We identify p to be -5 and g of x to be 0. Great. So what are the things that we need? We need to find the integration factor. So the integration factor here is mu equals e raised integral p dx, which is simply e raised -5 dx because p is -5. And if you integrate it, you will have e raised -5x. Keep in mind, when we did the integration factor, we did not throw in a constant. We kept it as 1. So we found the integration factor. Now let's move on to the solution. So the solution to the d was, or is, right over here, which is y equals 1 over mu. 1 over mu would simply be e raised negative integral p times dx. Integral of e raised integral p times dx times g of x dx and plus c. So what we have here is y equals 1 over e raised -5x I put the square bracket in the wrong place here. In the solution, so we are integrating that entire term inside the square bracket, and the 1 over e raised integral p dx is outside the square bracket. So that integral would result in a constant, and that constant should be inside the square bracket. That's a mistake that I made. So that is our proper solution. So we go back here and throw that constant back inside because it has to be inside. Plus c, and the integrating factor is e raised -5x, and g of x is 0, so 0 dx plus c. The entire term here goes away, so we have y equals 1 over e raised -5x times c, which is what, e raised 5x times c. So the solution here is some constant multiplied by e raised 5x. Now, if you make a direct comparison to what we did with the method of separable equation, that answer right there and that are one and the same. So do not make things complicated when you solve differential equations, especially first order linear equations. So if you can do it with the separable equation method, do it with the separable equation method, because that is easier. If you can't do it with the separable equation method, then we search for other methods. The entire purpose of this course is to come up with different methods to solve differential equations and understand them. So what is the existence interval for this solution? The existence interval, the solution would exist for all values of x that are properly defined, and we know the exponential function has a domain negative infinity to infinity, so the solution is negative infinity to positive infinity. Okay, moving on to the next one. This particular problem is not separable. No matter how hard you try, you cannot simply bring the y terms on one side and the x terms on the other side. But this is a linear first order equation, so we have y prime plus y equals e raised 3x. Make a direct comparison to our equation, which is y prime plus py equals some function g of x. That's what we have. So what is the value of p? P is simply 1, and g of x is e raised 3x. The first step is to find the integration factor. The integration factor is mu, which is e raised integral p times dx. And we know that p is 1, so we have e raised integral 1 times dx. We'll get e raised integral dx, which is simply e raised x. And again, we threw that constant away at the very beginning, so we don't have to worry about that. Now we can move on to finding the solution. The solution to the linear first order DE is y equals 1 over mu integral mu times g of x dx plus c. That c has to be inside the square bracket. So y would equal 1 over e raised x. That's what we have. Integral mu is e raised x times g of x is e raised 3x dx and the constant c. So y would equal to 1 over e raised x. Using the properties of exponents, the bases are identical, so we add the powers. X plus 3x is 4x dx plus c. And we know the integral of e raised 4x is 1 over 4 e raised 4x times dx plus c. Distribute the e raised x inside, or we could write it as e raised minus x and then distribute. If we distribute, we would have y equals 1 over 4 e raised 4x times e raised negative x dx plus the constant times e raised negative x. So again, using the properties of exponents, the bases are identical, add the powers. 4x minus x is 3x. Dx shouldn't be there. And plus c times e raised minus x. And that would be the solution.